Welcome to the Module 9, Time Series Analysis and Forecasting. The purpose of this chapter is to provide an introduction to time series analysis and forecasting. Suppose we are asked to provide quarterly forecast of sales for one of our company's product over the upcoming one-year period. Production schedules, raw materials purchasing, inventory policies, marketing plans, and cash flows will be affected by the quarterly forecast we provide. Constantly, poor forecast may result in poor planning and increased cost for the company. So how should we go about providing a quarterly sales forecast? Good judgment, intuition, and awareness of the state of the economy may give us a rough idea or feeling of what is likely to happen in the future. But converting that feeling into a number that can be used as next year's sales forecast is challenging. So, what is the time series? A time series is a sequence of observation on a variable measured at successive points in time or over successive periods of time. The measurements may be taken every hourly, day, week, month, year, or at any other regular interval. The pattern of the data is an important factor in understanding how the time series has behaved in the past. If such behavior can be expected to continue in the future, we can use it to guide us in selecting an appropriate forecasting method. To identify the underlying pattern in the data, a useful first step is to construct a time series plot, which is a graphic presentation of the relationship between time and the time series variable. Time is represented on the horizontal axis, and the values of the time series variable are shown on the vertical axis. So let's first review some of the common types of the data patterns that can be identified in a time series plot. A horizontal pattern exists when the data fluctuates randomly around constant mean over time. The stationary time series denotes a time series whose statistical properties are independent of time. The process generating the data has a constant mean. The variability of the time series is constant over time. A time series plot for a stationary time series will always exhibit a horizontal pattern with random fluctuation. To illustrate a time series with a horizontal pattern, consider the 12 weeks of the data in left table, which shows the number of gallons of gasoline sold by a gasoline distributor in Birmingham, Vermont over the past 12 weeks. The average value, or the mean, for this time series is 1925, or 19,250 gallons per week. The right figure shows a time series plot for the data in the table. Note how the data fluctuate around the sample mean of 19,250 gallons. Although random variability is present, we would say that this data follow a horizontal pattern. However, simply observe a horizontal pattern is not sufficient evidence to conclude that the time series is stationary. More advanced texts on forecasting discuss procedures for determining whether a time series is stationary, or provide a method for transforming a non-stationary time series into a stationary series. Changes in business conditions often result in a time series with a horizontal pattern that shifts to a new level at some point in time. For instance, suppose the distributor naturally expects to see a substantial increase in weekly sales starting in week 13. Left table shows the number of gallons of gasoline sold for the original time series and the 10 weeks after signing a new contract with the Vermont State Police to provide gasoline for state police cars. The right figure shows the corresponding time series plot. Note the increased level of time series beginning in week 13. This change in the level of time series makes it more difficult to choose an appropriate forecasting method. And now, what is the trend pattern? Although time series data generally exhibit random fluctuation, a time series may also show gradual shift or movement to relatively higher or lower values over a long period of time. If a time series plot exhibits this type of the behavior, we say that a trend pattern exists. A trend pattern is usually the result of long-term factors such as population increases or decrease, shifting demographic characteristic of the population, improving technology, changes in competitive landscape, and or changes in consumer preference. To illustrate a time series with a linear trend pattern, consider the time series of bicycle sales for a particular manufacturer over the last 10 years, as shown here. Note that 21,600 bicycles were sold in year 1, and then 22,900 sold in year 2, and then so on. In the year 10, the most recent year, 31,400 bicycles were sold. A visual inspection of time series plot shows some up and down movement over the past 10 years. But the trend for the bicycle sales time series appears to be linear and increase over time. The trend of a time series can also be identified by analyzing movement in historical data over multiple time periods. Seasonal patterns are recognized by observing recurring patterns over successive periods of time. For example, a retailer who sells bathing suits expect low sales activity in the fall and winter months, with peak sales in the spring and summer months to occur every year. Although we generally think of seasonal movement in a time series as occurring over 1 year, time series data can also exhibit seasonal patterns of less than 1 year in duration. For example, daily traffic value shows within the day seasonal behavior, with peak levels occurring during rush hours, moderate flow during the rest of the day and early morning, and light flow from midnight to early morning. Another example of an industry with sales that exhibit easily discernible seasonal patterns within a day is the restaurant industry. Sometimes, series include both a trend and a seasonal pattern. For instance, this table and figure show quarterly smartphone sales for a particular manufacturer over the past 4 years. Clearly, an increasing trend is present. However, the figure also indicates that sales are lowest in the second quarter of each year and highest in quarter 3 and 4. Thus, we conclude that a seasonal pattern also exists for smartphone sales. In this case, we need to use a forecasting method that is capable of dealing with both trend and seasonality. There are different forecast methods for horizontal pattern and trend pattern. So let's start by horizontal pattern. The simplest method for horizontal pattern is called naive forecasting method, which is to use the most recent data to predict future data. For example, we have this gasoline selling data right here. The forecast of the week 2, if we use naive forecasting, we use the week 1 value as the forecast of the week 2. And in this case, Y2 hat is equals to Y1, which is 17. And you can tell that in the week 1, we don't have any forecasted value because that's the start of our data. And then we can consider another method for forecasting the gasoline sales time series. Suppose we use the average of all the historical data available as the forecast for the next period. We begin by developing a forecast for week 2. So because there is only one historical data available purely to week 2, the forecast for week 2 is just the time series values in week 1. And thus, the forecast for week 2 is 17,000 gallons of gasoline. And then to compute the forecast of week 3, we take the average of the sales value in week 1 and week 2. And as a result, Y3 hat, which is the forecast value of the week 3, is 17 plus 21 divided by 2, which is 19. Similarly, the forecast for week 4 is 17 plus 21 plus 19 divided by 3, which is 19 too. In Excel, first of all, go to the practice and then download the gasoline Excel. And then we can go to the naive right here. And I've already provided you all the formulas, so you don't need to worry about this. For the naive, so we said the naive is equals to a last time series. So we can, here in the C3, we just type equals to B2. See, that's the forecast of the naive, that's the naive forecast. And then we just need to drag it down to the end. So this is the naive forecast. And then we can go to the average forecast right here. Alright, so the average forecast is equals to the average value from the start point to the value of the last point. So if we add the week 2, the start point is week 1, and then the end point is also week 1. So we will use the average function of week 1 to week 1. Okay, and then for the week 3, we have the average function from week 1 to week 2, correct? So in this case, we'll use the average function to calculate it from B2 to B3. And then the same thing for the week 4, we have the average of week 1 to week 3. That's for the week 4. Okay, so based on this, we can tell that the week 2, the start point is always there and never change. And then, but the last week, the end point of the time series always changed, and then it's changed with the sequence. So in this case, we can actually drag it down. If we want to drag it down, we have to make sure that the B2 will never change, but like B2 to B4 will always change, right? Because the start point should not be changed. So in this case, what we will do is we will make B2 as the absolute reference. So we add $sign right here to make it as an absolute reference, and then the endpoint we leave there because we want it to be changed. So right now, if we drag it down to the end, we can see that the B2 is always there, right? And then, but the endpoint is always changed to the last time series. And also you see that we have some of the time that has multiple decimals. So I don't like that. So I want to round it up to 2 decimals. So I will using the round function, round this up to 2. And then I will drag it down again. So this is how we calculate it. There are 2 forecast methods that are specific appropriate for time series with a horizontal pattern, which are moving average and exponential smoothing. These methods are capable of adapting well to changes in the level of a horizontal pattern. However, without modification, they're not appropriate when considering trend, clinical trend, or signal effects are present. Because the objective of each of these methods is to smooth out random fluctuation in the time series. They are referred to as smoothing method. This method are easy to use and generally provide a high level of accuracy for short-range forecast, such as a forecast for next time period. The moving average method uses the average of the most recent k data values in the time series as the forecast for the next period. Mathematically, a moving average forecast of order k is shown here. In the formula for the moving average forecast, yt plus 1 hat is the forecast of the time series of period t plus 1. Yt is the actual value of the time series in period t, and k is the number of the period of time series data used to generate the forecast. To use moving averages to forecast the time series, we must first select order k. If only the most recent value of time series are considered relevant, a small value of k is preferred. To illustrate the moving average method, let's return to the original 12 weeks of gasoline sales data. To illustrate how moving average can be used to forecast gasoline sales, we will use a 3-week moving average. Thus, the k is 3. We begin by computing the forecast of series in week 4 using the average of the time series in week 1 to 3. So the formula is y4 hat is average of the week 1 to 3, which is 17 plus 21 plus 19 divided by 3, which is 19. Thus, the moving average forecast of sales in week 4 is 19. We next compute a forecast of sales in week 5 by averaging the time series value in week 2 to 4. Because the k is 3, that's a 3-week moving average. So now we have week 4, week 3, and week 2. We will not include week 1 in our calculation. And as a result, week 5 forecast is 21 plus 19 plus 23 divided by 3, which is 21. And you can tell, since the k is 3, we have to use 3 weeks as the moving average. So the first 3 weeks doesn't have enough weeks to helping us calculate the average. So the first 3 weeks has no forecast. The forecast is started by week 4. Now let's see how to do the moving average in Excel. So keep the same Excel file. We go to the moving average sheet. And then to do so, we don't need to do any formula right here, but we need the tools helping us. So go to the data and we open the data analysis tool. And when this dialog comes up, we go find the moving average right here and then click OK. So we need to put input range, which is B1 to B13. Alright, so this is the original data set we are used for forecast. And then I highlight this a lot of times that since we included B1, but B1 is not the data, it is the column of the B. So that is the label. So if we included B1, we have to click the labels in first row right here. And if we didn't include B1, let's say if we start by B2 right here, then you do not need this. Okay, I highlight this multiple times. I wish you already understand. And next, we go to the interval. Since we said we set the k equals to 3, so we want our interval start by 3. So we hit 3 here. And for the output range, we will put it as C3 because there's no matter what, the first one will never have the average, right? So based on the case different, the moving average will start by either week 2 or week 3 or week 4. So no matter what, when we're using the moving average, you won't leave the first week forecast empty. Okay, so we click C3 here. And then we will click OK. So now you see that we have week 2, without any forecast, week 3 without forecast. And then so we have the forecast start by week 4. And then you can tell that the average of the week 4 is, if we see this formula right here, the formula of the week 4 forecast is the average of B2 to B4, which is week 1 to week 3. And that is what the formula that we used. Okay, so this is how you calculated the moving average. And right here, this is using the B11 to B13, which is week 10 to week 12. So this actually is the forecast for week 13. Now let's talk about exponential smoothing, which uses a weighted average of past time series value as the forecast. So here is the formula for the exponential smoothing, which is the yt plus 1 hat equals to alpha yt plus 1 minus alpha yt hat. So in this case, the yt plus 1 hat at the left side, that is actually the forecast value for the coming period. And then the yt is the actual value of the last time series, and then the yt hat is the forecast of time series. So actually, the exponential smoothing is to use part of the actual value plus part of the forecast value from the last time series to forecast the coming time series. And the smoothing content, alpha, is the weight given to the actual value in period t. And then the weight given to the forecast in period t is 1 minus alpha. So let's give you an example to show how this works. So this is the gasoline sales time series. To illustrate the calculation, we firstly can set the smoothing constant, which is alpha, as 0.2. So we're going to use 20% of the actual value and 80% of the forecast value to calculate the coming forecast value. So here, the first week actual value is 17. We were using that value as the forecast value for week 2 because there's no forecast value for week 1, right? And then to calculate the week 3, we can use both actual value of the week 2 and forecast value of the week 2. And then since the actual value of the week 2 is 21, so we're using 0.2 multiplied by 21. And then since the forecast value of the week 2 is 17, so then we were using the 0.8 multiplied by the 17. As a result, the forecast value for week 3 is 17.8. And then we can use the same method for week 4 forecasting value. Since we have the actual value for week 3 is 19, and the forecast value for week 3 is 17.8, then we can use 0.2 multiplied by 19 plus 0.8 multiplied by 17.8, so that we have 18.04. That's the forecast value for week 4. So this is how we do the exponential smoothing. Now, let's go to the exponential smoothing. For the exponential smoothing, we also need help from the tools. All right, so the same thing, we go to the data analysis, and then we found the exponential smoothing right here. All right, so the same thing for the input range. We have B1 to B13. And then we have the labels. So because we have B1, that's the column name, and that's the labels. So if we include the B1, we have to click labels. And now check here, we have dumping factor. So the dumping factor is not smoothing constant. So if we set 0.2 as the smoothing constant, and the dumping factor right here is actually the percentage we used for forecast values, which is the 1 minus the smoothing constant. So if we decided to use 0.2 as the smoothing constant, we have to input 0.8 right here, all right? Remember that. Okay, now we go to the upper range. So that is a little bit different with the moving average. When we're using the upper range for the moving average, we start by the C3, right? But for the exponential smoothing, we have to start by C2. Okay, so that is the little bit difference between the smoothing average and the exponential smoothing. So I put say 2 here, like don't get confused, and then we click OK, and you will see that we have all of the information right here. Okay, so if you go to the formulas right here, for example, for the week 3, we're using 0.2 multiplied by B3, which is the actual value, and then 0.8 multiplied by C3, which is the forecast value. So this is how we can create the exponential smoothing using the tools. And you can tell that the values are like the decimals for all of these values becoming more and more. So if you don't like that, you can highlight the column C and then go to the home, and then you can click this button. So this is how you increase or decrease the decimal, the amount of decimal. So you can click this button and make it only 2 decimals. And yeah, that's how it works. And so far, the 4 methods, which are naive forecasting, average forecast, moving average, and exponential smoothing. So these 4 methods are all for horizontal patterns. So the next step, what we're gonna do is we're gonna talk about how we can calculate the forecast for the trend patterns. So the linear trend projection is a statistical method used in time series analysis to forecast the future values based on a linear relationship between time and the variable of interest. So forecasting methods are appropriate for time series that exhibit trend patterns and show how regression analysis can be used to forecast a time series with linear trend. That's because if you remember the linear regression we learned from the last class, we always have an independent variable and dependent variable, right? So in this case, we will have time as our independent variable, which is x. And then any variable of interest would be the y, which is the dependent variables. So let's see this plot. So although the time series plot in this figure shows some up and down movement over the past 10 years, we might agree that a linear trend line provides a reasonable approximation of a long-run movement in this series. So we can use regression analysis to develop such a linear trend line for the bicycle sales time series. And because the simple linear regression analysis uses a linear relationship between the independent variable and dependent variable that minimize the MSE that we talked about last class, right? So we can use this approach to find a best fitting line to a set of dataset that exhibit a linear trend. In finding a linear trend, the variable to be forecasted is the dependent variable yt, and actual value of the time series in period t is the dependent variable. And the trend variable, time period t, is the independent variable. So we will use the following notation for our linear trend line, which is the yt hat equals to beta 0 plus beta 1 t, where the beta 0 is the intercept of the linear trend line and beta 1 is the slope of the linear trend. The Excel can be used to compute the estimated interception B0 and the slope B1. You need to download the bicycle Excel right here, and then we have to create the time index. And the time variable begins at t equals to 1, corresponding to the first time series observation, like year 1 for the bicycle sales time series. The time variable then continues to t equals to n, corresponding to the most recent time series observation, like year 10 for the bicycle sales time series. So thus, the bicycle sales time series t equals to 1 corresponds to the oldest time series value, and t equals 10 corresponds to the most recent year. So there is a very cocky thing here that the t is sometimes it's not actually the year. For example, we're in 2025. We will not use t equals 2025 because this is the real year. But the t here is actually actually the time index. That's the first time period, first time series, second time series, or third time series. It's not actually t equals to 2025 that's corresponding to this year. Does that make sense? So we want, no matter what kind of the year, the month, the day we were using in the real data, we want to create a time index to representing the first time series, like the first day or first month or first year until the most recent day, month, or year. So that's a time index. We're not using the real day, month, or year as our t in this linear trend pattern. And then we can use scalar plot to create it to find a simple linear regression equation. So we will highlight this, and if you are using the Mac, you can press Command. If you're using the window, you can press Alt or Control. So you press it, and then you highlight another cells, which is our dependent variable. And then you go to the scalar plot and created the scalar. Okay? And now what we can do is we can remove the grid lines and generate a trend line, linear trend line. So we can, here we can set the minimum to 15. We can set it to 20. So it's gonna be something like this. And then we can display the equation and the r square. So here it is the equation and r square. So the Excel output for regression analysis of the bicycle sales data is provided here. That's the same way we're gonna use as how we created a linear regression. So the estimated intercept B0 is 20.4 and the estimated slope B1 is 1.1. So we have a YT hat equals to 20.4 plus 1.1t. That is the regression equation for the linear trend component for the bicycle sales time series. And then the slope of 1.1, it actually indicates that over the last 10 years, the firm has experienced an average growth in sales of about 1.1 thousand units per year. And then to find the predicted sales, we just need to using this equation 1.1 divided by the time index and then plus the 20.4. So this is our predicted sales for week 1. And we're just dragging it down. Now we have all of the predicted sales. And if we assume that the past 10 years trend in sales is a good indicator for the future, we can use this equation to project the trend component of the time series. For example, when the t equals 11, which is the coming year, that we are trying to forecast the coming years, the sales value, we can use t equals 11 into this formula, and then so that we will have the y11 equals to 32.5. And so that means, thus, this linear trend model yields a sales forecast of 32,500 bicycles for the next year. Now, since we have the different method on forecast, we need to pick up the best method that fits the data the most. That is, to find out who has the best accurate for the forecast. So to answer this question, we will introduce several mirrors of the forecast accuracy. So this includes the forecast error itself, the mean forecast error, and the mean squared error. And these mirrors are used to determine how well a particular forecasting method is able to produce the time series data that are already available. So, by selecting the method that is most accurate for the data already observed, we hope to increase the likelihood that we will obtain more accurate forecast for future time series. The key concept associated with measurement forecast accuracy is the forecast error. The forecast error is the difference between the actual and the forecast value for the period t. The formula is arrow t equals to yt minus yt hat. So yt is the actual value and yt hat is forecast value. For example, for the week 2, when we're using the most naive forecast, we have the actual value of 21 for week 2, and we have the forecast value 17 for the week 2. And in this case, the forecast error is 21 minus 17, which is the 4. And then for the week 3, since the actual value of the sales in week 3 is 19, and forecast error for week 3 will equals to 19 minus 21, which is the negative 2. So in this case, the negative forecast error indicates that the forecast overestimated the actual value for the week 3. Thus, the forecast error may be positive or negative, depending on whether the forecast is too low or too high. So it is important to know that because we are using a past value of the time series to produce the forecast value for period 2, we don't have sufficient data to produce a naive forecast for the first week of this time series. As a result, there is no forecast error for the week 1. And then here are the forecast error calculation for all 4 methods for the horizontal pattern.
And same thing in average forecast, we use the same method as the true value minus the forecast value. And we drag it down to here. And same here, but be careful, we start by week 4, we're using the sales actual value minus the forecast value. So we only calculate forecast error till week 12 because there is no actual value in week 3. Okay, exponential smoothing, same thing. We use actual value minus the exponential value and drag it down.
You can tell that we're all using the actual value minus the forecast value, come up with the forecast error. And check about the bottom left, which is the forecast error of the moving average. And since we use the k equals to 3 in the moving average, so there's no forecast value for the first 3 weeks. And as a result, we only start to calculate the forecast error by the week 4. And then we will calculate the mean forecast error. So if we have m periods in our time series and k is the number of the period at the beginning of the time series, so we can use the sum of the forecast error divided by the amount of the forecast error we have. So for example, in this case, when we use a naive forecast, the total forecast error is 5. And then we have 11 forecast errors because the week 1 doesn't have the forecast error. As a result, the MFE, which is the mean forecast error, is 5 divided by 11 equals to 0.45.
Now, to calculate the mean value, we calculate the sum of the forecast error at first, which is the sum of this. So this is the sum of the forecast value. And if we use the formula to calculate the average, the mean forecast value, we will use the sum and divided by counts. We will count how many cells we have, right? And to minus 1 because that is k. And this is the mean forecast error, and then we would like to round it up to 2 decimal. So this is the traditional way to do it. And same thing for average forecast. We calculated the sum of forecast error and so we round it up at first, round it up to 2, right? And then we go in the between. We have E14 divided by using count all actual value minus 1. Yeah, so this is how we calculated the forecast value. Now for the moving average, have sum of the forecast error. So this is only from week 4 to week 12.
Since we use k equals to 3 in the moving average, so when we use the traditional formula, which is total error divided by the count of the forecast, that we have to be careful about that total count of the forecast value is total value minus 3 because k equals to 3. So that actually means the first 3 weeks has no forecast value. So a simple way to ignore this mistake is to use average function to calculate the mean value from D5 to D17, which is the method 1.
Be careful, the D14 is not our forecast error, that's the sum. So don't include D14.
Or you can use total error to divide it by the count of the D5 to D13, which is the count of the only forecast errors. So that is method 2. And method 3 shows the traditional formula method.
And the traditional way is, let's round it up to 2 at first. And then here it would be sum, which is D14 divided by count all actual value minus the k, that's 3. This is the traditional way to do so.
You can choose either method, all of them are correct.
So the same thing here, we have sum of all of this, and then we can use average to calculate the forecast error. And using the same logic, we can use average to calculate the forecast error in naive and also the average forecast. And here, same thing, do not include E14 and E15 because they are the sum and the mean forecast error we calculated before. So we can just use average right now. And yeah, if you want, you can run it up to 2. Same thing here. We use round, average, all forecast error, and now to be careful of the bracket. You will have a lot of bracket issue right here. Yeah, okay.
The other measurement tool used is mean squared error, which is the measure that avoids the problem of positive and negative errors offsetting each other, that is obtained by computing the average of the square forecast errors. Based on the table, the sum of the squared error is 179. Hence, the MSE, which is the average of the square of the forecast error, is 179 divided by 11, which is 16.27. So what we do is in column G, we will use E3 and squared. So this is how we use the squared of the E2, which is forecast error. And then we just drag it down to G13 and H13. So we have the every squared errors of each forecast error. And then what we will do is in G14, we calculate the sum.
Using the same way as the total value divided by count, or actual value minus 1. And don't forget to brackets. Okay, and then we can round this to 2. Or the easiest way we will do is we can use average function to calculate the forecast error, square forecast error, right? And then we can use round up. So it's the same thing. Okay, and then for the average forecast, same thing. We use E3 powered by 2, and I can just type average all of these arrows. Yeah, and that's how I calculated the average forecast error. And if you want to round it up, so we will round this up to 2. Moving average, here start by week 4, drag it down, calculate average squared error, and round this up to 2. Okay, same thing for exponential smoothing. It goes to powered by 2. Drag it down. Let me calculate average squared error. Okay. Yep. So this is how we calculated forecast mean squared error. And because of this is the best, so we can highlight this one, highlight this one, highlight this one, and highlight this one.
We normally use mean squared error to compare and select the most accurate forecasting method because it is a standard and reliable measure of how well a forecast model predicts actual values. So based on the result from last slice, the average forecast method has least MSE, which is 8.1. Thus, we can conclude that the average forecast method is the best forecasting model for this specific dataset. We can use the same measures like the forecasting error, MFE, and MSE to calculate the accuracy of a linear trend model for the trend pattern. So this is how we're going to do. Step 1, we calculate the forecast error using the same way. In another new column, we enable it forecast error and subtract the predicted sales from the actual sales, and then we can have the forecast error for that specific time index. Then we drag this formula down for all rows. And we use the sum function to calculate the total forecast error and then use the average function to calculate the mean forecast error. And then in another new column, label it squared error. We square the forecast error, drag the formula down for all rows, and then same thing, use the sum function to calculate the total square error, and use average function to calculate the MSE. Thus, the MSE of this linear trend model is 3.07. Now we should understand how we use the method we picked up to forecast for new time index. So for the horizontal pattern forecasting, we assume that the future value will follow the past value without any systematic increase or decrease. Thus, this method works well for stable data, but fail to capture trends. So this kind of the horizontal pattern forecasting only used for the short-term prediction, like in one time index. So to do so, you just need to drag C13 down to C14. So we drag the forecast value from the last actual value, and then the forecast value of the week 13 is automatically showed up. So this works for all of the horizontal pattern forecasting methods, but remember that it only works for short-term prediction, normally like one-time index. And on the other side, the trend pattern forecasting assumes a consistent increase or decrease over time. And this method uses mathematical methods such as the linear regression to extend the trend into the future. It is very useful for the long-term trend. So especially for couple time index in the future. So if you want to predict the coming 5 time index, you just need to forecast the value from index 11 to 15, and then dragging the formula down from, for example, from E11 to E16. So in this case, you will see that the forecast value for index 11 to 15 will automatically show up. So in this case, if you try to predict, for example, like the 15 or even 20, you can use this way to drag it down, or you can automatically find the time index and use time index within the equation to calculate the predicted sales for that specific time index. As a result, let me highlight again. The trend patterns works perfect for the long-term trend, and then the horizontal patterns only works for the short-term trends.